Hello everyone, this is a comment on the publication in the Journal of Nuclear Engineering titled Preliminary Core Design Study of Small Supercritical Fast Reactor with Single-Pass Cooling. The authors are Kyota, Uchimura and Akifumi Yamaji from Waseda University, Japan. The editorial is MDPI. The reason why I choose this publication is it's because I'm board reviewer of MDPI. And of course, this is not a top journal. So it's also interesting to see because otherwise it will not get a lot of attention. So let's go to see the abstract. I will read the abstract and then go a bit over it and make some final thoughts. A supercritical water-cooled reactor, SCWR, adopts a once-through direct cycle, which is compatible with a small modular reactor class SMR plant system. The core is cooled by supercritical light water, which does not exhibit phase change. So it means it doesn't boil, but undergoes large temperature and density changes. This is interesting because usually in most of applications, you don't consider the density change of water according to temperature. But here, due to the large temperature variation without boiling, it's significant. We'll see later. A superfast reactor, SuperFR, is a fast reactor type concept of SCWR. Unlike other SCWR core concepts, it adopts the single coolant pass flow scheme, in which the coolant passes the core only once from the bottom to the top without any reverse flow or preheating stages. In the meantime, reducing the core size tends to increase the core power peaking and reduce criticality. I'm not sure about the meaning of this. I guess reduce criticality means reducing reactivity of the whole reactor. But I'm not a nuclear physicist, so I'm not sure. Therefore, the key issues with the small SuperFR core design is reducing the core power peaking. Okay, core power peaking, I think it's the variation between the maximum and minimum power within the reactor. So the less homogeneous it is, the power distribution, the more the power peaking parameter. So it's not good. And achieving high average core outlet temperature with the single coolant pass scheme. This study aims to highlight the design issues through conceptual core designs of SMR class SuperFR. To evaluate the core characteristics, three-dimensional coupled core calculations are carried out. The proposed design with small foil assemblies, which are equivalent to those of boiling water reactors, attains a high core average outlet temperature of about 500 degrees, which is compatible to that of a typical large SCWR core design. So you see the main point of this is to see if we can further reduce the scale of these modular reactors, small modular reactor, without having the drawbacks of increasing power peaking and reduction of average outlet temperature. And for this, they use some numerical simulations, but this is a very preliminary stage of the study. It's not yet for design purposes. The introduction, it's interesting, but, I will mention that there is this Canadian SMR design that uses plutonium dioxide and thorium dioxide as a fuel. That's interesting. Cooled by supercritical light water and moderated by DO2. I guess DO2 is deuterium water. And we will just go through all this. Yeah, the power is around the 300 megawatts electric. So it's like a bit less than 1/3 of RBMK 1000 or the popular commercial reactors for nuclear production. So we'll jump directly to the design target. So they fix these targets. So outlet temperature higher than 500 degrees. And this is for thermal cycle efficiency. Below that, you will start losing efficiency. Average linear heat generation rate and operation cycle length. The operation cycle length is the time between fuel recharge. So after this time, which is 2 years, you need to stop the nuclear reactor, wait for it to cool down, and then change fuel assemblies or redistribute them within the core and add some new, and then run it again for 2 years. This is important because in these small nuclear reactors, to be cost effective, because they will be deployed in areas very far from civilization, maybe not civilization, but they will be put in Siberia, places which are not very accessible. So having the maximum operation cycle is critical for these small modular reactors to be economically viable for the applications they are intended. Then we also have this, very interesting. One of the criteria is the void reactivity coefficient must be below 0. So a positive void coefficient like the RBMK 1000 reactor is not acceptable. They impose below 0 because these small reactors can only be economically viable if they are inherently, how to say this word, by themselves they are safe. It means when something gets out of hand, you just walk aside, and if you don't do anything, they will just stabilize. So for this, of course, you need a negative void coefficient. A positive void coefficient, if you do nothing, it just gets exponential and has a critical runaway. And then we get into the model. They use some neutronic calculation that you can check in this reference. I already checked the reference 12. It's a 3 pages document with a lot of equations in which you have the neutronics and a lot of mathematics associated to nuclear modeling. It seems this is 2007, but it must be it's based on a previous edition, like from the 80s, the original equations. Okay, and there are several libraries that you can use for different models, for different applications. I will not go deep into this because I don't even understand everything. So here you have the neutronic, this reference we just checked. Then we have the thermohydraulics. So in the model, everything must be coupled because you have the neutronics in the fuel, in the nuclear reaction, and then you have the water that takes out the heat from the fuel pellets, and this behaves like a thermohydraulic system. And then we go into the core design, and you have all these parameters here. I will not read in detail, but basically they will test 4 core configurations. So each one has a different size, from 127 to 37 fuel assemblies. And you are also getting other parameters here, like the average fuel discharge batch number, which is in average how many cycles each bundle of fuel gets. Because we reuse fuel, after 2 years, we don't change all the fuel assemblies, we change some and we relocate the others. So in average, these are the number of cycles one fuel assembly gets. So the higher the number, the more fuel efficiency, the more economical you will be. This is also interesting, the average fuel discharge burn up. So you see, usually with a high average fuel discharge batch number, you get a higher burn up. So you get more gigawatts out of the same quantity of fuel. And here you see the diagram of the 4 designs. Is the power indicated here? Yes, here. So the big is quite big actually. Thermal power, this is thermal, not electrical. thermal is 1800, the RBMK 1000 is around 3000. So this is almost 2/3 of our RBMK 1000, and the smallest is 500 thermal. And you see indicated the fuel cycles. So you put the fresh fuel with more enriched plutonium or whatever the fuel you are using, uranium, thorium, but not all the material is feasible. So only one part is feasible. For instance, if you are using uranium dioxide, an enriched fuel element, when it's fresh, before starting the cycle, will have around 4% of enriched uranium out of all the uranium in the assembly. I'm not sure about plutonium, but I guess it's similar. And this is called reactor grade nuclear fuel. It's very different from weapon grade. For instance, the first weapon that was dropped in the Second World War, not the first one that was tested in the desert in the US, the first one that was dropped in Japan, which was the little boy, it was not an implosion bomb, it's the other kind. It's I don't know how is it called. It's a long, thin one. It was called Little Boy. That one had uranium core, let's say, with 80% of enrichment. So weapons need a much higher enrichment to be efficient. In reactors, we need around 4% in this kind of reactors, in a pressure water reactors, and even no enrichment is needed in CANDU reactors designed in Canada or in the original RBMK 1000 before the post-accident modifications. And then as the fuel burns up, burning up fuel not only means that you reduce the fissile material, but also some poison elements build up in these fuel elements. So the reason why you have this distribution is to avoid power peak, which we saw in the abstract of the paper. So getting the more reactive fuel in the middle is the one with third cycle, so it has less fissile and more poison. You get a more homogeneous distribution of power across the reactor. And you see here these 4 configurations. And I think this is a flaw of this paper. I will comment on this later. But it's not really a flaw, but maybe a slight weak point, because this is very design-oriented. You have to choose this configuration. For instance, you cannot... Here in the center, you need to put 7 third cycle assemblies. You cannot put 7.2, which will be the proportional correct value according to the scaling of this problem. So you are constricted by the discrete nature of this geometry, which makes the next results not very meaningful, actually. And here we have the average outlet temperature, which increases with the size of the reactor, which is outlet temperature, the higher the better. We have a more efficient thermal system. And here we have some colorful results of the numerical simulation, but actually this picture must be like 1 kilobyte. How did they compress this so much? And if you see, the core has an hexagonal shape, same as VVER reactors. This gets a better use of the space than square shape like the one used in Westinghouse designs. And because of the symmetries, you see this hexagon, so you can cut it like a pizza in 6 pieces, and you have 6 triangles, and they just simulate one, assuming there is symmetry. Actually, they could even cut once more, because there is the hexagonal symmetry, and then each triangle you could still cut it in the middle. It's an isosceles triangle, you cut it in the middle, you get 2 rectangular triangles. So actually you have 12 symmetries here. So if you really wanted to refine a lot this numerical mesh and get a more precise result, you could still cut it into half. Why they didn't do? I guess it's not really needed, because these kind of simulations are not that heavy. So, well, I don't know. And here we have some results. I will not go deep on this, but actually what they propose, increasing the average outlet temperature by, So the conclusion of this is, okay, we have a problem. The more we reduce the size of the reactor, the less outlet temperature we have, and we have more power peak, which is not good. How to solve this? How can we have small modular reactors which are more economically interesting for rural areas, Siberia, things like that, or even to put in vessels to go, these vessels that break the glass, to things like that. So they propose to reduce the size of the fuel assemblies. And they do a new simulations, and they show that the assembly pitch, which is the size of the fuel assembly, the bigger it is, the lower the average outlet temperature. And you see it's reducing from 480 degrees to 435 or so. And let's compare this to the previous chart. Yeah, so it's in the same scale. So this is very significant because this reduction of fuel assembly size compensates for the reduction of size of the actual reactor, assuming that everything else is linear. And then they propose a longer batch cycle. So instead of 3 cycles, they have fuel up to 5 cycles in the center here, which provides a better use of the fuel, I guess. And I will read the conclusions. The main issues designing an SMR class SCWR core have been discussed to propose SMR class Super FR with a single pass coolant flow scheme. The issues include, but are not limited to, raising the average core outlet temperature, reducing the power peaking, reducing the core pressure loss, increasing the operation cycle length, reactivity. Yes. Oh, I don't want to. And attaining negative reactivity feedback with the coolant density. And this is interesting also. It's a safety feature. Why it's selecting all the document? Okay, here. Reducing the fuel assembly size and increasing the fuel batch number are effective methods to raise the average core outlet temperature and reduce the core power peaking. By adopting small fuel assemblies, which are equivalent to those of BWR, the proposed design attains an average core outlet temperature of about 500 degrees, which is compatible to typical large SCWR design concepts. So, what he's saying here, I lost my point. Where was it? Reducing the fuel assembly size. Yeah, increasing the fuel batch number. Please don't over. Yeah. Okay. Increasing the fuel batch number. So you see here they propose this new batch scheme, and actually, if your problem is power peaking, if you put fuel with more cycles in the center, you can compensate for it. So that's what they mean with that. They propose a new batch scheme for reducing power peaking. They also propose using the smaller fuel assemblies, which actually already exist and are used for the BW reactors. And with this, they get a higher power not power output, temperature output, but because they also can achieve a lower peak, they can probably also get some higher power output. Yeah, so that's it. That's an interesting publication. Probably it will stay under the radar because this journal is really not top-notch. And actually it's also very new. It has only 6 or 7 publications. But it's interesting nevertheless. And I hope you enjoyed this. If you like my comment of this paper, you can propose other subjects or papers, and I will try to download the paper and make a video on it. See you in the next video. Bye.